And now I'd like to introduce the speaker. Brian Potter has been a research meteorologist with the Forest Service for 21 years. He began as a postdoc researcher in East Lansing, Michigan, studying weather patterns associated with large fires in the eastern U.S. His work focused on non-fire disturbances to forests such as tornadoes, windstorms, and thaw-freeze events in the late 1990s, before he moved back to examining fire-atmosphere interactions in 2000. In 2006, he transferred to Pacific Wildland Fire Sciences Lab to become team leader for the Air Fire Research Team, a position he held until 2012 when he stepped down to focus more on research issues. And with that, I will hand it over to Brian.
All right. Do we have my screen?
Yep, you're up.
Okay. Thank you, Josh. So as he said, my talk is going to be about plume dynamics or convective column dynamics associated with wildfires. This is Chapter 5 in the Joint Fire Science funded Synthesis of Knowledge of Extreme Fire Behavior. I'm going to start out actually by revisiting the definition of extreme fire behavior that we used in that study. The basic definition, which I'm not getting slide changes, we might have to restart this. There we go. Okay. The National Wildfire Coordinating Group definition of extreme wildfire behavior is the only one that really existed before we started doing this. And that definition is right here. You can see it. It contains a number of subjective terms. So it talks about high rate of spread, prolific spotting or crowning, strong convection column, and so on. And it's largely tied to management actions, which none of those characteristics make it a conducive, good definition for using in a scientific literature review. So we decided that it wouldn't hurt in any case to survey the community and about what they considered extreme fire behavior. So we did that. We sent out emails and we used listservs and so forth and solicited input from the fire management community on what they considered extreme fire behavior. And we got quite a laundry list, long list, and so we sat down together and we discussed the various issues or characteristics that had been sent in. And in the end, it boiled down to a definition that I think was pretty tractable, although it seems overly simplistic sometimes. And for the purposes of this review, we defined extreme fire behavior as fire spread other than steady state surface spread, especially when that spread involves rapid increases, either in rate of speed or intensity or something of that sort. Or another example would be going to a crown fire. So I want you to keep that definition in mind as I go through the rest of this, because in particular I'm going to hit on the steady state aspect and a little bit on the crowning versus surface spread. There are 4 topics that I'm going to focus on. Areas that are discussed a lot during conventional usage or common usage on operational fire situations. One is plume-dominated fire versus wind-driven fire. The second one is the concept of the adverse wind profile. Third, I'll talk some about stability and instability. And fourth, I'm going to talk about downbursts and the concept of plume collapse. To start out on this conversation, though, we need to have a shared understanding or a shared concept of what a fire plume actually is. And this is one of the figures from the synthesis and review, and it illustrates some of the key characteristics that are part of this. There's the most obvious and the visible one, which is the updraft. That's where the smoke is, and that's the hot, buoyant air rising up from the fire, accelerating because of its buoyancy. That air, when it leaves the combustion area, I should emphasize the red crescent in this image is the fire. We're looking at it from above to the side. So the fire produces the buoyant plume. To replace that air, there's air flowing in from behind the fire and from the flanks of the fire. So that's the arrows marked rear surface inflow and lateral surface inflow. There's also a fair bit of evidence from experimental studies, field studies, that shows there is what we've called a descending rear inflow for the fire. And that's essentially air that comes to the fire from behind and falls down to the surface or is drawn down to the surface by the remaining parts of the airflow. And that air coming from behind, it can be coming from Some indications are as low as 10 meters, as high as possibly 500 meters or so. We really don't know. There's very little data on exactly where it comes from. But that air can bring with it different characteristics from the air that was observed at the surface previously, so it's sort of a possible source of surprises. This image and this concept, I want to emphasize, this is sort of a time-averaged illustration. It smooths out the little eddies and the swirls and the turbulence and everything that can be found along fires. And so it's not the whole picture. And in fact, it's all the deviations from this that create extreme fire behavior. This is another illustration of the same thing, but viewed from above. There's the red fire region. You've got the inflow along the flanks, and some of the air eventually makes it around the fire. You often get little whirls at the front, and those can produce fire whirls or vortices. That's something that you'll hear about more if you listen to the webinar by Scott Goodrick and Jason Forthoffer on, I believe it's April 30th. They're going to talk about vortices and wildland fires. So this is, again, a time-averaged or a sort of a cleaned up version of what we think happens. I want to illustrate that point by showing this video. This was a metal fabrication plant across the street from my office last summer, and you can see in the plume these rolls and roiling turbulent eddies and everything in the various updraft speeds. You see pulses and so on. That's what we're really trying to capture here, and it's all of that variability that is the part we get in that definition of extreme fire behavior. It's a reflection of it. It's the non-steady component. It's the fluctuations, and in particular, if those lead to an increase in the intensity or the spread of the fire. So with that framework in mind and those sorts of caveats, let's talk about plume-dominated versus wind-driven fires. This dichotomy, this splitting of fires into these two categories, was based on work George Byram did in the 1950s. And he was motivated to do it by conversations and observations of fire behavior, about fire behavior that he himself had or that he had conversations with fire managers. And they noted that they were wary of fires in different ways when they behaved differently. In one case, the wind-driven fire, the fire was going in a predictable direction. It may be spreading very quickly, but it was going in a known direction, and it was spotting in that direction, and it was in that respect more predictable. But if the convective column was more vertical and taller, then more what we would now call a plume-dominated fire, they were less sure of some of the things they should be watching out for, and the fire's direction of travel could vary and things like that. So Byram was trying to scientifically analyze something that was anecdotally considered important. And in that process, he came up with the terms power of the wind and power of the fire. And power of the wind is kind of what you would think. It's how hard is the wind blowing. Power of the fire is a calculation that relates to the energy output of the fire. It's tied to the intensity calculation that Byram also put forward, which is related to rate of spread, fuel load, and heat content of that fuel. And when he did this, he was looking at the fires and trying to analyze how those two quantities related. And he considered the idea that a plume-dominated fire was when the power of the fire was actually more than the power of the wind. Conversely, wind-driven fire is when the power of the wind dominates the power output of the fire. And this is a scanned page from his original text on this. It's in a book. And in it, he talks about how a fire starts necessarily at low intensity, and it builds in intensity as the wind engages with it and fans the flames, increases the efficiency of the heat transfer to other fuels, and so on. So as the intensity increases, and that can happen because of fuels or topographic factors as well, but in any case, as the intensity of the fire increases, then the power of the fire increases. And you need wind energy to fan those flames, but then the power of the fire passes some sort of threshold and exceeds the power of the wind. Then you've gone to what he would call a plume-dominated fire. But notice you need the wind to build that intensity. And this leads to a sort of a cycle that you can have. I'll get to that in a second, but I also want to note that in other sections of this book, Byram emphasized that it is not necessarily the plume domination itself or the wind domination or wind-driven conditions themselves that are the danger. He saw the transition period between those two as the time of greatest danger because the characteristics of the fire's spread were changing. And so to revisit that concept of the winds in interaction with the plume, you start with wind and fuels and maybe terrain, but in any case, the other factors contribute to ramping up the fire's intensity, and that intensity is necessary to create a strong enough updraft that you get what we would call an upright plume. And when you get that upright plume, it is more able to sort of withstand the winds that are blowing against it, and they more blow around it. And that changes the fire's behavior somewhat. It stops running with the fire as much as it might have been before. It can also loft embers higher in that sense. But as the intensity dies down after that, which inevitably it's going to at some point, how quickly it dies down is the important factor here. But as the intensity tapers off and the plume weakens, you begin to allow the wind to take over again. So you now have a transition back to the wind pushing the fire forward. So you've got this back and forth. And as the wind takes over again, it could start fanning the flames again, and it could start the intensity back up and return you to plume again. This is the sort of back and forth that Byram was concerned about. If you have a howling wind, it's much harder for the intensity to get to that plume upright stage. If you have little or no wind, you're going to be in an upright plume situation the entire time. So Simard et al. Looked at the Mack Lake fire, and to my knowledge, they are the only group to have done a scientific application of Byram's power of the fire, power of the wind concepts to a case study. And for this case, they went through and they took quite an extensive bit of data after the fire. They went through and they did a post-fire fuels survey comparing burned area fuels with unburned nearby to determine how much fuel was consumed and what the energy output would have been. They looked at fuel moisture measurements to find out how much fuel was actually available and how much evaporation had to go on before it could burn. They took atmospheric soundings, the nearest and closest in time. They used these to do steady-state rate of spread calculations and intensity calculations. Again, it's the Byram intensity is equal to heat content times fuel load times rate of spread. And so they were able to calculate powers of the fire from that. They got power of the wind from the soundings. And what they found, even after they went to all this effort to calculate the most precise values for all of the input variables, was that the answer, which was higher, power of the fire or power of the wind, depended a lot on what altitude they were looking at and what time during the fire's duration they were looking at. And it didn't clearly allow them to identify stages or altitudes at which power of the fire and power of the wind were clearly dominating. The one time, if I recall correctly, that power of the fire exceeded power of the wind, it did so from the ground up to one height, and then it dropped off, and then it was higher again because of the wind profile. So this was a case, though, where they went out and they meticulously collected observations to tell them what the fire was actually doing and what those terms would have been. And they couldn't get a definitive answer. So, quick summary about plume domination versus wind-driven. The common usage of these terms does not generally address the transitional behavior that Byram was actually most concerned about. We seem to have fixated on the endpoints and not the middle ground where it's going back and forth. Observation or identification of a fire as one of the two categories out in the field is nearly impossible if you're at the fire line, partly because you can't see the vertical plume very well if it's up there. Calculation of Byram's power of the fire and power of the wind is basically impossible in real time. If you take S490, you'll be told that that is one of the standard things you're going to be taught, but if you pay attention to the class, you'll find that once it's mentioned in the objectives, it's never addressed again. Bottom line really is that situational awareness, paying attention to what the fire is doing and what it is likely to do in the near future, are really the only solution or way to address the concerns that this dichotomy, the power of the fire, or the plume-dominated versus the wind-driven fire, was intended to consider. Adverse wind profiles were more of George Byram's work. He was a really fundamental researcher in the early days of fire-atmosphere interaction research. For this piece of his work, he looked at 17 large and notable fires across the United States, and he pulled up the atmospheric soundings from the nearest upper air observation site. Now, I should note there are only about 90 to 100 observation sites across the entire United States, depending on what year you're looking at. And so some of those fires could have been a couple of hundred or a few hundred miles from the nearest observation site, and they could actually have been upwind or downwind. He didn't have the luxury of only taking an upwind sounding or something like that. So he examined 17 fires and he looked at the wind profiles, and from that he identified 9 basic profile types, 6 of which he associated with extreme fire behavior. The most dangerous, in his opinion, was what he classified as type 1A. He referred to that as one of the most dangerous types from the standpoint of personal safety and erratic or unpredictable fire behavior. And you'll notice this kind of fits with his description in the power of the fire, power of the wind calculations. You've got the strong winds at the surface that can fan the flames and create the intensity, but they decrease with height. Now, the other types, the other 8 of his 9, are shown here, types 1B and so forth. It's the type 4, 4A, 4B, and 4C that he considered not contributing to extreme fire behavior. Some of these aren't that easy to distinguish, and it's not clear why he separated some of them into different types. So like type 2A and 2B, they're very similar, but he clearly saw some distinction, and he talks a little bit about that in his publication. But again, what do you have when you're out in the field? You don't usually have that profile, but what is commonly taught as far as an adverse wind profile in practice is that the speed is greater than 18 miles an hour in the free air at the fire's elevation. By free air, we mean you're not standing on the ground holding a kestrel or an anemometer. That would be measured with a radiosonde or a balloon of some sort. And along with that speed at the fire's elevation, you have wind speeds that are decreasing with height for several thousand feet above the fire, with the possible exception of the first few hundred feet where the wind speed may actually be increasing with height. And that was simply an acknowledgement that right near the ground, the vegetation and the terrain create frictional drag that slows the wind at the ground, and it picks up speed as you get away from that. But overall, the point was that the profile is decreasing above that. Now there's one case study, or one research paper that looked at whether Byram's adverse wind profiles occurred on fires other than the ones he started from. And that was Brotak in 1976, who looked at 62 large and notable fires, and I'm being vague about large and notable because those authors were. But Brotak looked at 62 fires, and of those 62 fires that he looked at, only 1/3 of the fires had a jet or a profile similar to what Byram identified as adverse. So that's not a great track record. If they're really that worrisome and they constitute 6 of the 9 profile types he identified, then only occurring on 1/3 of fires isn't very promising. Bottom line on adverse wind profiles, Byram included a lot more than just wind profiles in his 54 paper, especially more than just wind speed. He was particularly concerned about the direction changes with height, and he said that the direction profile is an extremely important part of the complete wind profile. He also talked about stability in that paper, but we only ever discuss his adverse wind profiles or the low-level jet. The premise is scientifically unproven. In fact, the only study looking at it seems to disprove it, but hey, let's get more observations and see if we can find out more clearly what's going on. Even if we have this concept, the data to apply it is not readily available in the field. In the end, plume tilt, flame direction, and the direction spots are landing in are the clearest signs you can get of how a wind profile is affecting the fire. Stability or instability. Foley 1947 was the first publication to look at or to mention the possibility or the concept that atmospheric instability is important for wildfires. Foley focused on the fact that unstable atmospheric conditions lead to a lot of turbulence, and that turbulence creates gusty, variable fire behavior. Crosby in 1949 looked at instability, or proposed instability was important again. In this case, he looked at a more organized influence on the fire's behavior, and he discussed an overall mechanism. And what he was talking about was the idea that if you have an unstable atmosphere, there's less resistance in the atmosphere to that updraft from the fire. So without resistance, the updraft is stronger. So with a stronger updraft, you have to have stronger inflow into the updraft column, and that inflowing part influences the intensity just by fanning the flames. You also, with more instability and that increased wind flow at the surface, you get more turbulence. And one of the consequences that can develop along with that turbulence and that strong updraft is fire whirls or vortices. And you'll hear a little bit more about that, or actually a lot more about that, if you listen to the presentation by Scott Goodrick and Jason Forthoffer on April 30th. Instability is really a type of stored energy. Think of it like putting a rock on top of a cliff. A rock atop a cliff has stored energy, potential energy we talk about, and yet it's just sitting there. It's not doing anything. And it's only when that rock falls and converts that stored energy to energy of motion that it can have an impact, that we worry about it. So just because there's instability, it's not the instability itself that affects the fire's behavior. It's what it turns into, whether it turns into an organized updraft and inflow winds that are sort of smooth and steady state, or whether it's mostly turbulent energy. The odds are it's a combination of those two in almost every case. High instability allows a strong updraft, which creates stronger inflow, and with that inflow comes more turbulence and more erratic fire behavior. Downdrafts and downbursts. I should note that this presentation is deliberately a bit shorter than some of the others have been because I wanted to allow a lot of time for questions. Downdrafts and downbursts. This is an illustration of a thunderstorm, a fairly contemporary model of what the airflow is in and around a thunderstorm. Now in a fire you don't have a lot of these features, but you do have an updraft. And you cannot have an updraft without having some sort of downdraft. Now, generally speaking, the downdraft is not as intense as the updraft in terms of concentrated local winds. Sometimes the downward motion of the atmosphere is spread out over a large region and is very slow compared to the very focused, strong updraft. But every fire has a downdraft. I want to point out that a lot of you have seen, in fact, on one of the earlier webinars, there was a discussion about the Fire Weather Handbook that Schroeder and Buck wrote in the 1970s for the U.S. Department of Agriculture. These are images from that. They talked about the 3 stages of a thunderstorm and extended that to discuss relevance to fire circulations. This is an extremely out-of-date mental model of how a thunderstorm or a fire updraft works. The dissipating stage and these graphics would only apply in a very, very, very specialized case where you have almost no wind or wind shear. As such, don't think of the fire as doing this. Think of it more like that previous image. And you can find that previous image on the recorded webinar if you need it later. So what's the difference between a downdraft and a downburst? Well, all fires create an updraft of some magnitude, and every updraft has to have a downdraft associated with it. But like I said, that can be of varying intensity and cover smaller or more localized regions. A downburst is an intense, short-lived, localized downdraft. When that downburst hits the ground, the current of air fans out much like water hitting the bottom of your faucet, and that results in sudden shifts in the wind direction at the ground and basically an increase in the wind speed around the fire or around the downburst on all but the upwind side where it's pushing against the prevailing wind. Along with that shift in wind direction and the increase in wind speed, you get an abrupt drop in temperature and an increase in humidity. Just to reiterate, a downburst is not just the same as a downdraft. There are always downdrafts, there are not always downbursts. And there are actually technical classifications in meteorology for what type and what intensity of a downburst. Downburst dynamics. Upward instability that we talked about earlier is driven essentially by heat, whether that heat comes from a fire or from the sun. Downward instability in the atmosphere is primarily moisture driven. What happens is you have precipitation at some height above the ground, and that precipitation falls into dry air. When water passes through dry air, the droplets start to evaporate, and with evaporation comes cooling. That gives you a cold air mass or a cooler air mass above warmer air, and gravity pulls that colder air down more strongly, and so you get a downward sinking blob of cold air. In addition to the evaporation, you actually also get frictional drag from the raindrops, and so they drag the air with them. So as long as there's cooling and moisture, you can get increasing downdrafts, but that happens over a localized area in general where the precipitation is falling. And this is another reason that other image is out of date, because if the precipitation is falling straight down from where it came up, it's just going to kill its own updraft and the whole thing's going to die. So those don't last. Those, if that ever happens, it's because there was no wind and it's very transient. In essence, greater instability, greater downward instability can produce stronger downbursts, and we can calculate estimates of downward instability. So the key elements in the atmosphere that will give you a strong downburst are a deep dry layer near the ground for all of that moisture to fall through and evaporate, moist convection, a moist updraft with water droplets in it so it can carry the water upward and then it can fall back through the dry layer. You need a strong plume to carry the water upward and to keep it up there. The bigger or the stronger the updraft, the larger the water droplets it can hold up before they fall out. You need wind shear so that the precipitation falls outside the updraft column. You need downward instability, which is sort of the summary of all of those factors in many ways. It's also important to note that this situation, many of you have seen virga or fall streaks. They're the shadowy, look like wispy cloud coming out of the bottom of a cumulus cloud. That's virga. That's the precipitation falling out of the cloud and evaporating before it reaches the ground. Evaporating before it reaches the ground is exactly what can cause a downburst. So even when you have virga, you don't always have downbursts, but you can. The one case that was documented with a downburst leading to fatalities, well, I shouldn't say that actually, because we now have more than one case where we believe that downbursts were involved in fatalities. Unfortunately, we have a fair number. This was the first one, though. It was the Dude Fire in June 1990 near Payson, Arizona, and it was documented by Goins and Andrews in a 1998 paper. And in that case, we have a deep dry layer, which is shown by the V in the temperature profile on the right and the moisture profile on the left there on the sounding diagram. I've highlighted the dry layer in yellow there. There are weak winds in this case, which is in a way a little bit surprising that you would get a strong downburst, but there is a little bit of variation in the wind direction, so you could be getting the enough tilt to drop the precipitation outside the updraft. They estimated that the height of the convective updraft and the plume was 11 kilometers, so you certainly have a strong, tall updraft to transport the water upward. And the downward instability, which is again sort of the combination of that dryness and the temperature profile, is fairly high in this instance. And the consequence was that a downburst occurred and it pushed the fire ahead on what had been a flank. There's another piece I should mention here, and that is that downbursts, because they are cold, dense air, flow downhill. And that is one of the things I've heard cited as causing partial cause of the fatalities here, was that the downburst the airflow ran downhill, and even when the fire crew ran down a creek drainage or something like that, the cold air pushed the fire with them. So the usual rule of don't run uphill, go downhill if you're trying to escape a fire, unfortunately can be thrown out the window if you're running or dealing with a downburst. Plume collapse is the next topic. It's related to downbursts. I want to show two short videos to begin this. And let me pull those up. First one is the Chellasley wildfire, which I believe was in Canada. It might have been Edmonton. This is a time lapse. I want you to look at the way the plume is behaving there at the top of the cloud. You can see the fire down on the left a little bit, but focus on the top where it launches up and boils over, and then it drops back down, and then it boils up again, and it drops back down. You can see it rising and collapsing, rising and collapsing. The other video is actually the Drumheller water fountain on the campus of University of Washington. And I want you to look at the same sort of behavior. Notice the top of the plume of the fountain isn't always the same height. It rises higher sometimes, it falls at times. It rises higher on one side and then it falls, or it rises all the way, and so forth. Okay, let me see if I can get that. Okay. And then one more video. This is a time lapse of a wildfire in California some years ago, and I've shown this to many groups, and I've always forgotten the name of the fire, so apologies. Don't bother telling me because I forget it again anyway. You can see the fire, if I can get my mouse to wake up again. You can see the fire is over here and over here right now. You'll see some more activity over here in a moment. But look at the way the plume is rising up. There's that other activity. You can see the plume launching up, and you can see the smoke going up and blowing off with the wind. And notice that there's a lot of wind here, because look at how that's leaning over. And yet, if you look right at the fire, it goes back and forth in terms of how that plume is leaning. Now, right about now, we're getting more energy from the fire, and look at how the plumes are reaching up deeper. And here's the big push. Notice how it launches up and then it falls back down, launches up and it falls back down repeatedly during the time of this thing. But is that plume collapse? I would argue that is not at all plume collapse, because the fire is still going at the ground. It is still churning out massive amounts of energy, and it is still maintaining a plume. What's more likely happening is what we would call in meteorology overshooting turrets or overshooting plumes. And in essence, that's like a rock on a spring, or a mass on a spring bouncing up and down. If you release it from the ground, it'll overshoot the equilibrium height, going higher than it would normally stop because it has momentum. And when it gets up there, it will slow down. Eventually, it'll start to fall back down because it's too high. It'll fall down, but it will not fall back down to its starting point. It will fall part way down, and then it'll have overshot again, and then will move back up. And each time it oscillates, it goes a little less far. It ends a little closer to the final equilibrium level. And so watching these videos and seeing the top of that turret launch that high looks to a casual observer, and remember, that was time-lapse, so most of the time that will be happening very slowly. But overshooting can look like plume collapse, but it's rarely reflected by changes in winds at the ground. And again, if you watch that video, that last one in particular, the overshooting was well downwind of where the fire actually was in most cases. Now, it could overshoot and come over another flank of the fire, but it's rarely coming back down where the fire that generated the overshooting plume was. So plume collapse, the term, is very visually strong, but in reality, I have been looking for years now for conclusive evidence, video or accounts that show that a whole plume collapsed. I've got a couple of anecdotes related to slash piles, but that's it. Downbursts are really the behavior of concern at the ground. It's not what's happening at the top of the plume that matters so much. And a true collapse of the plume would require a rapid decrease in fire intensity. That's not saying it can't happen. It can happen in that sense, but the fire intensity is what drove the collapse more than the collapse driving the decrease or the change in fire intensity. All right, let me take a quick sip of water and then I'll wrap up here. So, in summary then, plumes and extreme fire behavior. Plume domination versus wind driven. Scientifically, it's a theoretical concept and a theoretical set of equations, but they are unproven and difficult to prove in the field. Adverse wind profiles are not well supported by the evidence in the cases where they have been looked at after their original publication, and yet the term and the idea are heavily referenced. Instability, there is a connection there between instability and fire behavior. It is known to tie to turbulence at the very least, but just how the instability manifests to affect the fire is a bit unclear. Some would argue very unclear. Downbursts? Downbursts are definitely killers. Dude fire, Yarnell Hill is attributed to downburst activity. I don't remember the name, but there was a fire in Florida where a downburst from a thunderstorm quite a distance away, the outflow pushed the fire flank and fanned it up and killed some firefighters. Plume collapse? I consider plume collapse to be dangerous terminology because it evokes such a strong image, and yet it is not quite what would be worrisome about fire behavior. So what I just described is basically sounds like I'm throwing all of this out the window in terms of what it can do for you in fire behavior, but I'm not. So here's what I'd like you to remember as you listen to this webinar or rewatch it or whatever. First of all, transitions between intense and wind-driven or deep plume fires, or the cycling between those, between wind-driven and plume, or vertical and leaning over plumes, or whatever way you feel is clearest to indicate it, is what Byram was concerned about. It's the transitions, not a constant steady plume or a constant steady wind-driven fire. A tilted or twisting plume, heading and backing behavior that vary along the fire line, and the direction of spotting or changes in the direction where spot fires are predominantly landing are indicators of the wind profile. In particular, mid-range spotting, which is affected by the winds up to higher levels than just short-range spotting, mid-range spotting and changes in that direction from the direction of the fire's progress can be a very good indicator of what direction the winds are above the ground and how strong they are. Instability in the atmosphere leads to turbulence and fire whirls, and again, fire whirls will be Jason and Scott's topic in a few weeks. Also remember that downbursts require a strong tilted column with a deep dry atmosphere, and that virga or fall streaks are a sign of potential downbursts. And overshooting plume tops are common, but they don't mean the fire will change behavior. And I felt like I ought to offer some sort of summary, profound closing comments, and so I came up with these. Plumes are as much a reflection of the past and the present fire behavior as they are a cause of it. So cause and effect can often get muddled. Think about the fact that the plume came from the fire. It can feed back on it, absolutely. But what you're seeing in the plume may be more a reflection of what has happened than what is going to happen. Scientifically, plume dynamics is by far the hardest piece of fire behavior to study. We have spent well over 100 years studying fire behavior, and arguably 80 of those years were focused on how the fuels affect the fire's spread and intensity, and if anything, how the weather affects the fuels. We have spent precious little time or energy or money trying to get at what is happening in the plume of the fire and how that affects the fire. And that's largely because it is exceptionally hard and dangerous to get that data. And the plume that you really want to study is the one no one is going to let you light. Bottom line, lookouts and situational awareness are the best and sometimes the only tools available when you're out in the field to assess plume influence. And finally, we've got time for questions, but probably not time for all of your questions, and you probably don't have all of your questions right now, so I will leave you with my email and my phone number. And please, if you have anecdotes or observations or questions, feel free to contact me, because this is where I get most of the valuable information about what I should be studying. And we will go to questions, I guess.
All right, thank you, Brian. That was a very good presentation. It's appreciated. There are a few questions that have come in now, and I imagine more will come in, so we'll start with the first ones we got. The first question is from Larry Kazir. For purposes of capturing video of the evolution of a plume column, from which direction would be most useful to researchers? Upwind, downwind, crosswind?
I would probably argue crosswind, partly because when you get downwind, you start to get the smoke in your face and you can't see quite as much. When you're looking from an upwind direction, you can't really see the sides and the lean of the column if there is any such. But we're very limited in what we can extract from just one camera view. And there have been some attempts to do stereo photography of smoke columns and get ideas of what's going on. But there's a limit to that as well, because you're only seeing the outer surface of the plume. You can't see into the plume with photography. But if you are going to set up a camera and get plume video and send it to me so I can do something with it, crosswind is probably the most useful for something like that.
Next question is from Jeremy Sauer. Given the relatively low cost of radiosondes, I'm not sure if I said that right, are these deployed as a standard procedure in the field? Could these provide more wind speed, directional shear observations?
Yes, radiosondes are now released much more commonly than they used to be. Because the cost has gone down, they are not always released. If I'm not mistaken, they come as part of the package that an incident meteorologist brings with them. So any fire where they have an incident meteorologist, they may have a radiosonde set up that they could bring with. And absolutely, those provide wind speed and directional shear observations at the site they're released. That's usually the base camp, or if you're lucky, the IMET knows of a site closer to the fire front or more representative of average fire conditions they can go to release the radiosonde. But the frequency they can do that with is also limited by their obligations to be doing other things as well. But it is definitely a piece that's out there now.
Okay. Mike Conley asks, the size class of fire stops at G, 5,000 acres or more. The study you talk about was done in the 70s. Is that study relevant to today's fire behavior, considering that many fires are commonly far exceed 5,000 acres?
Oh, is the study relevant, considering we now have much bigger fires? Yes, it's relevant because it's the only window we have into what might be happening. Yes, it's relevant because even a 300,000 acre fire is usually not burning along the entire perimeter, and so you get sort of pieces that might each be acting more like one of those 5,000 or smaller acre fires. Is it relevant? No, because to a degree, the subjective "which fires should I look at" question that Brotak asked and that Byram asked and that actually Don Haynes asked when he created the Haynes Index, they asked fire managers and state fire officials, tell me the fires that were problems for you. And so there's a lot of human evaluation that went into those. So that would be the only part where I would start to say they're not relevant. I wouldn't even say they're not relevant. I would say they need to be taken with a grain of salt.
Okay. Next one is more of a comment. This is from Daniel Borsum. He says the 8th Street fire in Boise in 1996 was episodes of plume collapse induced by outflow boundaries from thunderstorms disrupting the wind flow around the plume.
If I can get video of that, that would be great.
Okay.
And I see the comment above that from Michael Rode. So if there's a way I can, actually I'm going to write down that email because I don't know if I'll have them later.
Okay. Next question is from Marianne Jenkins, and she says, adverse wind profiles are heavily used in reference. Can you give us some examples of this?
Of the fact that they are heavily referenced?
Or just examples of adverse wind profiles?
I can't give you specific examples of adverse wind profiles because I question whether they actually are relevant and can be quantified in that way. There were a lot of assumptions Byram made when he created those profiles, and I have scientific problems with the way he did some of that. He did it because that was the only way he could do it then, and so I don't fault him for it, but I would not do it that way myself, and if I had the time and the resources to redo what he did, I believe I would find very different results. As far as how they are heavily used and referenced, talk to a group of IMETs or fire behavior analysts or read some fire reports, and you will get plenty of references in many cases to, we have an adverse wind profile today.
Okay. Next question is from Jeremy Sauer. Is there any possibility of partial plume collapse? Shouldn't hypothetical partial plume collapse or downburst really be categorized as density currents, which could affect fire behavior?
I like just classifying them as density currents. That's great. That works very well. I also like the idea of that you ended up referring to hypothetical partial plume collapse. I'd like to see that as an acronym frequently used in the field. No, I'm not serious about that, obviously. But you can, that overshooting, depending on how high up it is, there's always the possibility that overshoot and then rebound could lead to some circulation effects at the fire. But it would have to be a very low equilibrium height, which generally means a very low intensity fire, and it would have to be a stable atmosphere to push it back down hard, and it would have to be weak winds to allow the partial collapse or the upper portion of the plume to drop down in the vicinity of the fire itself. Now you could, I suppose, have portions of the plume coming off of the flanks in particular that would drop down or that would interact with the main head of the fire. But you're getting into such complicated 3D mental images that I don't want to venture there any further.
Next question is from Jeremy also. Are overshooting plume tops indicative of rapid changes in fire intensity at the ground?
Yes, they are a reflection of previous changes in fire intensity most of the time.
Okay. Next question from Gary Curcio. For fire managers or F-bands, what would you consider situational awareness pertaining to fire weather that we can ascertain from the National Weather Service as intel, i.e. upper dew point depression, instability, position, and curvature of the upper level trough, etc., in regards to position of your wildfire prescribed fire?
Okay, I'm reading that to make sure I get the gist of the actual question. The main features that you're going to get from the National Weather Service or from an incident meteorologist are going to be related to the stability profile. A good incident meteorologist and or F-band is going to have a sense of how that wind profile, how the winds expected on that day will interact with the local terrain. For example, if you're going to have the winds channeling up a canyon to a heavy fuel region, you should expect you've got serious potential for the winds and the fuels and the channeling to create a high intensity fire that will shift to some more plume-dominated behavior later. But again, if the winds aren't pushing it, it's not going to develop that. You need both. I'm trying to think, if I were told I could ask for 3 things from the Weather Service or from Intel, I definitely want the instability. I would want to know whether I had a deep dry layer that could contribute to downbursts. And I would want to know if there was significant rotation in the wind profile with height.
Okay. Okay, so the next question, or he says this is more of a comment, it's from Fred Scheffler. It's been my experience that plume-dominated columns collapse when the fuel bed or beds feeding the column thin out or are totally reduced. For example, heavy down, deaden down, and timber to grass. Heavy deaden down and timber to grass and/or rock slides. Once the fuel source is gone and/or drastically reduced, the columns collapse. You refer to a true collapses requiring a rapid increase in fire intensity. Some of the most remarkable column collapses I've witnessed were those in the 1988 Yellowstone fires in Montana and Wyoming and the Rodeo Chetasky fire in Arizona. These were also in light to moderate winds. Thanks, Fred.
Well, as he said, that was more of a comment than a question, but I appreciate the insight, and I don't disagree with some of the things. So, for example, I disagree with your life experience. I'm not saying that. What I'm saying is that what you described as going from heavy fuels to drastically reduced fuels, yes, that would associate with the rapid decrease in fire intensity one way or another. You don't necessarily get anything coming back down to the ground, though, to then influence fire. If you don't necessarily get that just because the intensity going up decreased. Again, if the downward motion compensating for the updraft is spread over a large diffuse region and is very weak, then losing the updraft is going to weaken a very benign downdraft. But the light to moderate winds, yes, like I said, there are some slash pile cases where I was told and have heard about the downburst or the plume collapse, and I don't dispute those. It's when you have light winds and the plume or the debris in the column can fall back down and the downdraft can occur at the fire that you have concerns.
Okay. The next question is from Nicholas Jolie. Brian, you touched on plume dynamics as being a major feature of fire behavior. We need a better understanding of energy release at the surface and how this translates into plume dynamics. That is how the fire combusting at the surface affects the behavior of the plume. Here in Australia, rising and falling plumes contribute to spotting, particularly where wind shear is strong and the atmosphere is dry. Terrain and wind shifts also contribute to spotting.
Yes. That will be part of my next talk, and thanks for joining, Nick. Good to hear from you. And I should also give a little credit to Nick. That opening slide with the jet plane in front of the plume, that was one that Nick showed me from the Black Saturday fires. And it's a perfect illustration of the interplay between wind and plume, because those fires would not have occurred without the intense winds at the ground, and yet the plumes they created were astounding.
Okay. The next question is from Jason Forthofer, who's one of the presenters coming up in a month or so. And he asks, why would a true column collapse require a rapid decrease in fire behavior? It seems any hot gases released from the fire would ascend eventually to their equilibrium in the atmosphere, mostly regardless of the momentum/buoyancy produced below. Imagine an instantaneous puff of hot gas ascending rather than a continuously emitting plume.
Jason's exactly right, and I guess that's the point I was trying to make, is that a puff of hot gas will ascend, and it'll do that oscillating behavior around its equilibrium height. The only conceivable way to get that collapse to occur at the ground, collapse, where the whole vertical column falls back down, as in that 1970 Fire Weather Handbook illustration, that requires more than just buoyant gases coming out of the fire. That requires something to almost push the gas back down, and that would be more of a downburst situation. And as one of the earlier questions pointed out, it's a density current issue.
Okay. Next question is from Gordon Springell. Fire running over increasing or decreasing topography, how does this affect plume domination?
Oh, well, if the fire is running uphill, which is, I'm going to interpret that as increasing topography. If the fire is running uphill, it generally reaches higher intensity, and that's going to allow more energy release and a more powerful plume. Again, I would be wary of plume domination, because really in that case I would say instead of wind-driven, it's almost terrain-driven, allowing the intensity to increase that then creates a more vertical plume, and when the fire slows or reaches the top of that ridge or slope, it's gonna subside again. So it's all an interplay of these factors, and you can't ignore the wind or the terrain only to focus on the plume. it does interact with the fire in varying ways. And the dichotomy, what I want to push back against is the idea that you should look at a fire and tag it as one of the two types, and one is worse than the other. An exercise I've done at times is to ask people to list what are the factors that are of concern when you're dealing with a wind-driven fire, and then list the factors that are of concern when you're dealing with a plume-dominated fire. And I've done that about 5 or 6 times, and almost every time the lists are very, very similar. There are just a couple of other factors that come up with plume-dominated that don't come up with wind-driven. And they're, in a sense, that suggests the distinction is not what you should be worried about.
Okay, the next question is from Jose Luis Duce Aragues. Hopefully I didn't screw up your name too bad there, Jose. And he says, after the 2012 large fire in Santa Fe National Forest, New Mexico Cerro Grande, I think that's more likely the Los Conchas fire, I'm thinking. Do you think plume collapse can be produced by just the opposite, by a great increase in fire intensity?
No, I don't think so, because again, I think that when you release that, when that energy pushes the air upward, the air is immediately being subjected to turbulent mixing that reduces its buoyancy, and it's being subjected to just frictional drag. So the cooling, basically, and the drag reduce its energy, so it will overshoot, but as it continues overshooting, it slows down more and loses more energy, and it oscillates. And even if you increase the intensity in that simple model, you're not going to increasing the intensity or decreasing the intensity isn't going to allow it to come back to the bottom. That would require something to push it back down. It's kind of like if you think of bungee jumping. When someone bungee jumps off of a bridge, they go all the way down and then they stop and then they come back up. They never come all the way back up to where they jumped off, fortunately for them. We wouldn't be doing bungee jumping if that did. It's basic conservation of energy and dissipation of energy in a system like that. They stop at the relaxed length, basically, of the bungee cord. They're doing an upside-down plume, and they don't hit the platform, fortunately.
So Phil Dupree asks, would it work sending a drone into the plume, cheap and safe?
If you can get data from the drone on the right quantities, then you could get some information from some of these things. Craig Clements and I did a first test of this quite a few years ago. We actually put instruments on a radio-controlled airplane. There weren't drones back then that we know of now. We put radio-controlled or radio-sonde components into a radio-controlled airplane and flew it through the plume on a prescribed burn. We did get some information from that, but we found that the sensors didn't respond quickly enough to the conditions, and so it was a little bit ambiguous what we were seeing. But that was as cheap and safe as you could get, basically. It was a $300 or $400 radio-controlled airplane. It survived the updraft, but it didn't give us quite as much information as we had hoped.
Okay. Sort of a related question. Neil Leroux asks, how can we create support for organizing large observational campaigns to actually study plume dynamics on large fires? This seems like a pressing need, especially including mobile radars to look inside the plume.
Combination of mobile LiDAR, which I know you're familiar with, Neil, and photographic techniques. I think those are the two most promising because you can combine them to get more comprehensive around the fire behavior from the photography and within the plume from the LiDAR. You're going to need some soundings around it. It's an intense field campaign. If you're familiar with the RX Cadre project, that was the biggest fire campaign the U.S. government's done since Project Flambeau in the 1960s. What you would really need, if you were to do a one-off to answer the questions about plume dynamics, would rival RX Cadre, if not exceed it.
Okay. The next is a comment and a link to a YouTube video. This is sent from Leland Tarnay, and I know some people can't see the questions and comments, so I've typed this in, and hopefully I'll send this out to everybody so you can see it. But he says this is a a video from the rim fire done by Jonathan Byers, a Yosemite National Park tech.
All right, we'll take a look at it later.
Yeah, everybody can take a look at that later on your own time. Next question is from Joseph Vaughn. Have you seen the following efforts in coupled MET and fire, for example, WRF-S fire modeling, and how well do you think it is capturing plume dynamics or behavior, and how well for fire behavior?
I have seen and followed to a degree the WRF-S fire and the CAFWE and the Fire Tech and the Walden Fire Dynamics Simulator work. Those are all what are classified as coupled fire atmosphere models. I think they may capture some plume dynamics. I have reservations about a couple of those models and how they portray how they calculate the fire behavior. I'm not going to go into that here. That's a whole other conversation. But I also know that you should be able to glean some good information from numerical models that don't, in fact, include explicit coupling with the atmosphere. Just a hot plate simulation can tell you a fair number of things about what the plume actually would do. And how well do they capture the fire behavior? That goes back to my first point, that that's a whole other conversation.
Okay. Scott Nutt asks, is 3D modeling occurring in plume research, more specifically with the plume overshooting principle?
3D modeling is occurring in plume research. I don't know if anyone is specifically trying to look at questions of plume overshooting.
Okay. Jeremy Sauer asks again, you mentioned that instability may be important. Unstable conditions are primarily observed during the daytime. What about particularly dangerous nighttime blow-up scenarios? What aspects of meteorology influence these?
My first thought on that question, Jeremy, is that nighttime blow-up scenarios can be a consequence of a fuel and terrain interaction more than an atmospheric influence, but they could also be driven to a fair extent by synoptic weather events. So if you had a front come through or a sea breeze, land breeze sort of transition, things like that can happen regardless. There's also some evidence in the Black Saturday fires. Michael Reeder at Monash University has some fascinating analyses that suggest that there was basically an atmospheric wave near the surface trapped against a frontal system coming inland, and as it moved inland and nighttime fell, the wave was able to run ahead of the actual front, and that wave's transition or passage over a couple of the fires was associated with blow-up conditions there.
Okay. Marion Jenkins has a question. I think it's in reference to her earlier question. I'm trying to go back and... oh, adverse wind profiles. That's right.
Yes.
Okay.
How are adverse wind profiles heavily used?
Right. So how are adverse wind profiles heavily used, and how are they heavily referenced?
Basically, they're the IMET, and I am not an IMET, so I have to put on another hat and sort of remember specific conversations. My recollection of the kinds of things I have heard are suggestions that, well, we have an adverse wind profile today, so we should be watching out for more intense fire behavior. That may be the extent of it. And when you say heavily referenced as opposed to used, I'm not sure what you mean. If you're talking about research literature, I can't cite any specific papers. I think, honestly, most research papers have forgotten and left behind the idea of those specific adverse wind profiles.
Okay. Daniel Borsum asks if radar data of plume fires would help provide data for research.
Yes, much like LiDAR data would.
Okay. Clifton McKay has a quick comment. He says the Chellaslee fire you mentioned identified as being near Edmonton was actually located in northwest British Columbia. And Jeremy confirms that he was talking about nighttime conditions. Next question is from Diego Calderoni. Has any research been done in studying the mass of large plumes? Given their mass, they would have less reaction to the surrounding air?
Again, it's a matter of we don't really have any data within those plumes. There's an entire community of people studying the type of updraft or the type of plume referred to as a pyrocumulonimbus. It's a type of fire plume that's exceptionally intense and reaches the top of the troposphere, pushing smoke and ash into the lower stratosphere. Those are generally the biggest plumes you've got. They are definitely a sign of the fire's behavior, but they are more, again, a sign of what the fire has done than what the fire is about to do. And you're right, they are sort of, by a surface area to volume argument, they are less influenced by the surrounding air. So there's not a lot of research on how those plumes affect the fire's behavior at the ground.
Okay, next question is from Clara Casada. Do you think firefighters in the fire line could underestimate plume activity as a sign of fire behavior? Do you think we/firefighters have enough information in this sense?
Not quite sure what you mean by underestimate as a sign of fire behavior. I think that watching the fire's behavior and the plume's behavior both, and the plume behavior because of how big the plume is and the smoke near the ground, I think that goes again to the fact it's really the lookouts and the spotters and the aircraft that have the best perspective on the plume activity. And that needs to all be rolled together with what's being seen at the ground. The person on the fire line is most able to see the flame lengths and the smoke coming up right near the ground and the spot fires being ignited and things like that, the rate of spread near the ground. And you've got to focus on what you can see, and what you can see lays ahead of the fire. How much information the person on the line has, I personally don't know, because I've never been on the line of an active large fire in that sense.
Okay. Next question from Jeremy Sauer. Might not adverse wind profiles, especially with respect to what Byram was studying, be characteristic of low-level jets or linear/nonlinear mountain waves?
Wind profiles, I mean, might the wind profile be the characteristic of a low-level jet? The low-level jet was more characteristic of some of the adverse wind profiles Byram identified. But the question of mountain waves, that's another question really altogether, because that also involves stability conditions and a number of other factors, I guess.
Okay. I'm trying to get through some of these here. We still have quite a few more to go. I know it's getting late, but I was trying to get through them. If a fire is producing pyrocumulus in low or no wind, does that have potential for column collapse? That's from Larry Kazier.
It has the potential for the debris in the column to fall back in the fire, and yes, it can influence the fire if there is little or no wind. If you have pyrocumulus, which means you do have water condensing at the top of the updraft, then there is some potential for that water to fall into the updraft and slow it down and cause sort of a feedback mechanism. I would still be hesitant to call that column collapse, because unless the fire is... Column collapse implies that the air that went up is coming back down, the whole thing, when you talk about collapse. And you've always got the potential for a portion of air to come and hit the fire from above. But it is almost never going to be the entire column. Even if the energy output at the bottom is shut off, the hot air from the fire previously is still going to rise. You're just going to stop feeding it. If you think of... Oh, no, that's a bad analogy. I'm not even going to go there. The other constituents in the updraft, basically the solid and liquid components, when the updraft starts to dissipate, and it will dissipate from the bottom first because that's where it's driven from, the liquid and the solid particulates in the updrafts can start to come back down. And only in as far as raindrops fall and have enough distance to build the momentum and to cool the air will they cause a downburst of some sort. But the conversations I've had with people about spot fire, or about slash pile burning and things of that sort, and jackpot fuels, those really suggest that what is happening is more a matter of the debris showers out because the updraft that was holding it up weakens. But the updraft didn't die. The plume didn't die. The air flowing into the fire did not shut off.
Okay. The terminology of adverse wind profile, plume collapse, favorable wind profile, plume dominated, wind driven, etc. Should not this be revisited and straightened out? Favorable wind profiles, i.e. Brotax wind profile, produce large wildfires. That's from Gary Curcio.
Yes, it should be revisited. That was largely what we were doing in the synthesis and review. We revisited it, and the conclusion, at least in terms of the literature, the scientific literature, was that most of these things are weighed. They've gained a certain level of legendary status in the operational community, and they are arguably, and I'll add the Haynes index to this quite readily, they are used far more extensively and in far more situations than the original scientists would have endorsed or would have applied them themselves. And yes, you're right. Wind profiles that Brotak would have considered favorable can produce large wildfires.
Okay. Go a couple more here. We still got quite a few questions to go. These are one of the most number of questions I've seen in a Q&A session. So maybe we can get some people to contact you outside the webinar.
Please do. We'll get to your question.
We have a couple more though. Darren Klebo asks, are you implying that in order to get strong downward moving air, a downburst, to come to the ground, you need to have some type of moist convection, i.e. evaporative processes?
To get a downburst, yes, you have to have moist convection. To get strong downward moving air, that is a different question and can be caused by a number of processes, including channeling, synoptic events, and other things.
Okay. Jeremy Sauer's got another question. Actually, Jerry's got quite a few questions here. Could soot loading lead to heavy air parcels? Do you think temperature and soot loading are equally affected with respect to buoyancy forcing by entrainment of cool, clean air?
Soot loading is a very, very, very weak influence on air buoyancy. The weight of the soot is in the parts per million quite often, at the very least, or at the very most, usually parts per thousand. So it is not a significant influence on the weight of air parcels. It doesn't come close to the effect of the temperature on making them buoyant. As for the effect of entrainment, it more or less, it affects temperature to a degree that the buoyancy is reduced, but since the soot had little effect, the entrainment has little effect on the effect the soot has.
Okay. Next question is from Michael Delegacios. It is known that the plume generates its own wind near the ground. How does this wind affect fire behavior?
Primarily, the updraft of the plume causes a stronger inflow. That inflow fans the flames and essentially increases the efficiency of the fire heating and igniting new fuels, so it spreads faster, more or less. And it also brings with it increased turbulence that can cause variable fire behavior.
Okay. Another question from Jeremy Sauer. We'll make this one the last one. There's quite a few questions left. I think if it's getting late, and I think there's somebody that's using the webinar account after this one, so we probably need to get off. I'm
gonna suggest that Jeremy call me.
Yeah, Jeremy has a lot of questions here, a lot of really good ones.
This is great.
Yeah, we'll do one more. This is from Jeremy Sauer. If a buoyant air parcel only oscillates around equilibrium height, how does one explain moist convection leading to cold pools and downbursts?
That is an excellent question. It shows a pretty complicated understanding of what I was describing, so either you knew this well before you came in here, or I did a pretty good job of explaining some of this. The air parcel separates from the moisture in the case of the downburst. So the air parcel itself may actually go on and do that oscillatory behavior around its equilibrium height, but the rain has fallen out of that particular bubble of air and gone onward through other air to create the downburst.
Okay. All right. Well, thank you, Brian. This has been a very good presentation. I know there's actually quite a few more questions left. If you would like to email them to Brian. I believe his email is right up there on the screen now. Yes, it is. Email and telephone number. And hopefully you guys can continue this conversation. But thank you for a very good presentation and a lot of information, a lot of really good stuff here. It's appreciated. And thanks to everyone for coming. Brian is going to be presenting again on March 12th, I believe. March 12th, is that right?
Yes, I think that's it.
On spot fires. So another good informative webinar coming up in a couple weeks. Thanks, Brian, and thanks everyone for coming.
Thank you.